Hey everyone, and welcome back. This was TBTL CTF 2024. I enjoyed the CTF last year, and I enjoyed the CTF again this year. Very nice and simple CTF, good challenges. There's no Discord, but maybe that's a good thing. No drama, just straight poning. For this video, I'm going to be covering these 4 web challenges, these 5 pwn challenges, and this one was a miss challenge. Yeah, I'm ending 24 hours early. We're moving tomorrow from Sedona to Salt Lake City, so it would have been fun to do some of the reversing or MISC or crypto, but I just don't have any time. With that, let's get started. The first challenge is Butterfly. This was a JavaScript reversing challenge. It says there's some sort of secret embedded in the page somewhere. So if we view the page source, we'll see some interesting looking JavaScript down here. It's also interesting to note that crypto.js was loaded in. So you can copy that JavaScript out and try playing with it for a while. First, it's good to take it to one of those online deobfuscators, and they'll clean it up a little bit. After you do that, you'll see a couple of these ASCII to binary calls, which is it's a base64 decoder in JavaScript. If you take these, this one decrypts to or decodes to secret is a very good secret or something like this, and this one was also decrypted. I already replaced it, but it decodes to this crypto, JS, AES, decrypt, ciphertext key. So we can kind of assume that somewhere in here there is a ciphertext payload. This is the key. We can just look at it, what it is real quick. I think it was this is a very good secret or something like that. Secret key is very secure, and we need to find some ciphertext. If you play with it, it's doing this weird thing where it's like calculating all these characters from this or something like that. And so you can just console log all the characters out. So to do that, I copied over the HTML into my own personal inner HTML, copied over the deobfuscated JavaScript and just put it in there. And so for this for loop, I just thought it looked interesting, so I figured I would save it. So for each one of these characters, I just append it to this out variable. So then we can run it locally. So localhost 8000. If we open up the console, we can print it out. So we have this. So this looks like some sort of ciphertext. If you base64 decode it, it's just a mumbo jumbo. So we'll use the crypto.js decryptor to decrypt this text. So use crypto.js. We give it the ciphertext and the key, and we get out the flag. It says TBTL, this is not secure storage. The next web challenge is Talk to You. For this one, we're given a website. I'm going to load it up in Burp. So if you click through the links, you'll notice something interesting in the URLs. We see this page is equal to about.html. So that hopefully makes us think of a local file inclusion. So we're going to take that, HTTP history, we'll copy this over to repeater, make sure it's still working, and then we'll see what files we can grab. If you play with it for a bit, eventually you'll find there's a flag.txt, one directory up. So we'll send. If we go all the way down, it says the flag is in the SQL database, SQLite database, database.SQLite. We say, okay, sounds good. Database.SQLite. We'll grab that one. And we get the flag. It says TBTL, typical database usage. So fun. The next challenge is R&D for your data scientist. For this challenge, we're given a URL and 2 download files. So if we go to the URL, we have this random matrix generator. And so the way this app works is we can ask for a matrix here. That's going to return a matrix of random numbers. But when we make a request to this service is going to make a request to the backend service. The backend service is going to generate the matrix for us, and the very last row is going to be the flag. When that gets passed back to the frontend service, that service is going to look for a row that has the flag, and if so, it's going to remove it. And so our goal is to trick it so that it returns a CSV of some sort that doesn't have a flag row. I'm not sure if I did it the intended way. I did it abusing delimiters, and I guess if there's a delimiter here, that would make sense. But you can also do some sort of injections with pandas data frames. So maybe that was also the intended solution. I'm not too sure. But anyways, so we can make a request. So I'm going to ask for this. I'm going to say C1 and C2. Delimiter is equal to comma. We're going to generate, and we get the CSV. There's nothing exciting about it. I might even have one over here. Yeah, data.csv. So it generates something that looks like this. So just 10 numbers and then a bunch of random numbers, and we can add as many columns as we want. But if we open it up in Burp Suite, actually, let's go look at the code before I show the solution. There's 2 files. I just put it into the same file, and I just renamed the other service to G on this file, so then I only had to spin up one server when I was testing. But like I said, this is the front-end request that comes through. We get to pass it this form. Like I said, it's going to make a request to the backend. And then after that, these are my print statements. It is going to grab, so this is the data frame column values. So there's the 0th column and the 1st column. And then it's going to filter through our data frame. So just the pandas data frame, and look if any of them are equal to flag, it is going to ignore that row. And so what's happening is the backend's returning, I forget exactly, but it's like, I think it's not a number, and then it says flag, and then it's like TBTL fake flag, something like this. So it's going to grab this entire column, and if any of these rows are equal to flag, or the fields are equal to flag, it's just going to delete this entire one. Not delete it, but just filter it out. Cool. And then it returns it. Sweet. This was that backend request that generates the CSVs that eventually get returned. So it's just going to generate all the columns based off the data. So the number of columns, the column names. It's going to do some filtering on the column names so you don't use these forbidden words. Like I said, I'm pretty sure you can do data frame injections, but that's not what I did. And then you can join all of the columns together. You get to specify the delimiter, which is interesting. The delimiter on the web app only allows 3 of them, these 3, but you can specify anything you want. And then, like I said, at the very end, it generates an extra row with the ID of not a number, a string flag, and then the actual flag string. So the way I ended up solving this challenge was, let's take this, we'll go to generate, we'll send to repeater, is we need to trick it so that it doesn't find a column named flag. And so the way I did this is, let me just relook at it, flag, cool. On the CSV parser, it is going to read in a CSV. By default, this accepts delimiters of commas because it's the CSV comma separated values. So what we're going to do is we're going to specify one of our our column as C1 comma, and then go to C2, and we'll say our delimiter is underscore. So let me just run this real quick. Cool. So what we get back, it's going to generate underscore delimiters for the actual table, but the front end parser is going to be looking for commas, and there is a comma here, maybe C1. There should be one here. So we have this delimiter. So it finds 2 columns, but I'm guessing the second row is completely empty because there are no delimiters there. So the second column exists, but there's just nothing there. And so all of this data belongs in the first column, and so it doesn't get filtered out, and it never matches this flag condition. Again, I don't know if that's the intended solution. It seems kind of like a cheese, but it worked. And so we have TBTL, data science is not for Rockies. And the final web challenge is Mexico City tour. Blah, blah, blah. We're given a URL and a download file. So for this app, we can search for the distance between 2 cities. It does say that the database contains a city flag, which is kind of interesting. So for this, we're given the source code, and thankfully it is very small. So the index route is going to make a Neo4j query, and it is going to match all the stations. So in Neo4j, we have nodes that have, I think this is label, the station label. And they have 2 properties or fields, ID and name at least. Then when we do a search route, it's going to take the start and the end. It's going to look up those nodes by ID, and then it's going to calculate the distance between them as BFS, save it as P, and it's going to return the size, and so the number of stations in between these 2 places. So presumably, as these nodes were loaded in, they specified some sort of relations, and so they can calculate the distance between them. So we have a Neo4j injection challenge. We control start and end. So we have 2 easy injection points. It's also important to know that the only information that we get back out to the web service is the distance on the first row, and it has to be an integer. So cool. So this challenge was mostly like an exploration challenge, in my opinion. Like you're supposed to figure out where the flag is. It was kind of hard to leak information. Most likely I did something wrong, but I thought that I checked for negative IDs at the start, back when this challenge had no solves. And it didn't return anything with negative IDs. So you find out like just through playing that there's like 162 or 163 of these. So I tried to see if there's anything above 162. Oh yeah, oh actually, sorry. I took all the station IDs and I saw that there we go. We have 163. So I tried, is there a -1 station? Is there a 163 station? Neither of those worked. And then later the negative ID did work. So most likely just being dumb, but it's also possible maybe if you were also stuck before the challenge had solves that maybe the station was missing. Again, most likely I'm being dumb. But after a while, I came back. I think I worked on it last night, and then I came back this morning, and then the -1 station worked. Again, probably just me making a boo-boo in my query, but the -1 station worked, and then it was much simpler to solve at that point once you know what you're looking for. Like I said, we're doing injections into Neo4j. So this is the query we're making. Let me copy this up. And these were the different injections I guess I was playing with to find something interesting. I guess another thing to note is Neo4j, they have this like load from CSV that you can use for exfiltrating data. I couldn't get it working. Again, most likely I'm a dum-dum and doing something wrong. Maybe it was disabled for this. I don't know. So I ended up doing a blind injection. So I would do a query, I guess where to start with. First off, I would just see if I could match like different IDs. So start, I would do like, again, like I said, -1, for example. I would try, large numbers. Once I eventually saw the -1 the next morning, that's pretty obvious where we need to go. So we have a -1 station. From there, you can also query on the keys and properties. So I wanted to see, is there anything interesting on all of these nodes? Again, we don't have much of an info leak, just an integer. So I would just see how many keys are on a matching node. And so this injection would read, return node 1, and then with the keys on that node as keys, and then return the size of keys as the distance field. And so then we'd find out there's only 2 keys. The same with properties. You'd find out that there's only two keys, 1 label. And so you can do stuff like that. Eventually, like I said, if you do the -1, you'll find out that it has, I think, 3 properties, and then you're on the right track. From there, my queries are all over the place, but I guess I started doing queries like this to see what the last field could be, because they don't tell you that it's flag. So I was doing little regexes with a match all to see like if it was city, because they say it's a city flag, I believe, with a city flag. So you would think it would be city or something like that, but eventually you find out that there's just a field called flag that only exists on one of the nodes. Cool. So once that's the case, you know that you want the ID, the node that has an ID of -1, and it has a field called flag, and we can perform regular expression searches on it. And if we have a match, it's going to return the -1. And if we don't have a match, it's going to return an error or an unknown because it didn't match anything. And then from there, we can just start doing a blind error-based leak. So I just go character by character. So I start with the beginning of the flag. We know it starts with a TBTL. This is a match all character because you don't want brackets in here when you're doing a regex match. And then by character, we can pretend I don't know what this is. But it's going to start with A, and then B, then C, then D, and see which one matches. When we get a match, it's going to return a -1, which is, return the ID as distance. So we get the -1 response. Otherwise, it'll be unknown, and you just go character by character, just your very standard sort of blind error-based injection. Eventually, you get out the full flag, and it is, where is my graph hidden? So, yeah, pretty fun challenge. The first pwn challenge was averages. For this, we're given a netcat port and 2 download files. Thankfully, we're given the source, which is always much appreciated. There's 3 functions. So we have main, it's going to call read flag and then vuln. As part of read flag, it's just going to open the flag, read it, and then close, which seems kind of silly, but if you know the bug, it makes sense. Then it's going to call the vuln function. The vuln function is we're going to enter in 20 numbers, and then it's going to calculate the average of those numbers. And that's it. So 2 very odd functions, but if you put them together, it leads to a fun bug. And the bug, I don't know if there's a name for it, but I guess it's like stack reuse or uninitialized memory. So when we call this read flag function, it is going to read the flag onto the stack. Cool. When the function leaves, so the stack pointer is pushed back up, but the flag is down here somewhere. And then when we go to the vuln function, it's going to allocate int score. So this is 4 bytes each. And this is so 4 times 20. We have 80 bytes here. It is then going to overwrite, or it's going to occupy the same memory as where the flag was. And so because of that, instead of when it asks us for a score and it's going to go down and insert those scores, if we insert a invalid character, so it's expecting a decimal, but you can do like a period, or maybe not a period, but a plus sign or a couple other characters, it just won't touch that memory, but it'll still add it. So that's useful. And then at the very end, it'll return the total score divided by 20. So what we can do is we can just go through character by character and set everything equal to 0 except for the uninitialized memory that we're interested in, and eventually we should leak the flag. So we'll start with the first one. We'll do a period or an invalid character so it doesn't touch that 4 bytes of memory on the stack, and then the rest of the stack we're going to set to 0. And then when it calculates the average, we just multiply it by 20, and that's what that integer was. And then we'll do it for the second integer and the third integer. This is the solve script I wrote. I'm just doing standard pwn tool stuff. So pwn tools, more pwn tools, pwn tools. Here I'm defining a leaks variable. And so for each of those 20 scores, I don't think we need all of them, but I'm going to connect to the remote host. And then for each of the player scores, if the player score is equal to the chunk that we want to save, we're just going to put a plus there so it doesn't get clobbered. Otherwise, we're going to clear it out with a 0. And then we're going to grab the score at the very end. We're going to multiply it by 20 because it's divided by 20. And then we add it to our leaks variable. It's an integer, so you can just do a long to bytes, or you could probably unpack it too. And then we print it out and we close. So we can run it. Cool. So Python 3 solve.py. Wow, it is very slow. So for the first one, we're sending a plus. Oh my gosh, that's slow. It needs to make like 400 requests, so we're not going to wait for that. But you saw the first one was a plus, the rest are zeros. And so the first 4 bytes on the stack is all zeros. Like I said, it's just going to go through 4-byte chunk. Eventually, the flag will be decoded, I guess, and you get this. TBTL, eat your veggies, initialize your darn variables. So, fun. The next challenge is a day at the races. May the fastest code win. We're given a netcat port, a Fibonacci.c, a primes.c, and a server.py. So you might be able to guess from the title of the challenge that this is a race condition challenge. And if you guess that, you are correct. So for this, just a background on the code, there's a server. You're allowed to submit source code and it'll compile and run it with the time, but it only allows source code that has the hash of either this or this, which is the given Fibonacci.c and primes.c. So on the surface level, it looks impossible to run any program except for those two. But in this code, there's a timing attack, so we can bypass that sort of protection. Here's the main function. We get to give it a file name. It's going to check the file name. I think it just needs to be lowercase characters and a period or something like that. It's going to define a path. Then we give it the contents of the file. So if everything was working correctly, this should only be the contents of Fibonacci.c. It's not that exciting, just Fibonacci function. Fibonacci.c or the other one. So it'll base 64 decode our input, and then it'll save it to the file path. Cool. Next step is to compile and run it. So it's going to calculate the hash of the file. It's going to calculate the path. Then it's going to call GCC on it. And then it is going to call the program. Cool. So as part of the solution, so maybe you can kind of see where the timing attack is coming in. We can have two different processes interacting with the service at the same time. And we're going to start the first one, and we're going to insert a legitimate Fibonacci.c sort of program. And so it's going to pass all the checks. We'll have a Fibonacci.c. It's going to save it as Fibonacci.c. Up here, it's going to compile Fibonacci.c.exe. And then right here, it's going to call Fibonacci.c.exe. Cool. What we can do right before this call happens, we can insert a new one, and we'll call it this new file. We'll call it Fibonacci.c.exe, and we will save it right here. But it's going to fail the compile time check, but we don't really care about that. Since it's on disk, this one's going to execute our new and evil malicious Fibonacci.c.exe, which is just going to be a bash script. And then we have a shell execution on the box, and we can do whatever we want. The challenge authors were very nice too. So when we insert our malicious one, there's no delay between, no significant delay between our input and when it gets saved to disk. Whereas in here, there's all these slow print calls. So it's going to do a slow print, compiling, and then it's going to compile our code. And then it's going to do a slow print running. So in between when it compiles our code, because we still want it to be valid code. And then we're going to wait until it starts typing out running ... And I think we have like a couple of seconds here before it'll call the actual exec call. So the actual timing is very generous. You get like a couple of seconds or something like that. To see what the exploit actually looks like, I'm using pwn tools, even though it's not really a traditional binary exploitation challenge. It has very useful network capabilities. So we're going to open up those two network ports. So we're going to set up the good file. The file name is going to be sloppyjoepirates.c. and we're going to start setting up the second evil process. We're going to call it sloppyjoepirates.c.exe, the new file, but we're going to wait to actually send the contents. So our good payload is fibonacci.c, and then we can put our evil payload in exploit.sh. I read both of those in. I do the base64. I guess I don't really need to print it. Then we send the good payload, and then in the good thread, we're going to wait until it says running. And so this happens right here, right before it actually executes the script. And right before the script is executing, we're going to overwrite it with our evil payload, and it should run and give us something juicy. So if we run it, Python 3 solve.py. I guess I should probably also show my exploit script. My exploit script was just wget, it's going to call to a webhook, and then cat out the flag and base64 it. So let's open that up too. I think at first I did like a LSLA to see what files exist. And then eventually I saw there was a flag.txt. And you can just pipe that to base64. Make sure you specify base64 with 0. Otherwise it does that like weird new line thing, which is kind of annoying. All of them, they all send individual characters at a time, so that's why we get that really nasty output. But we get this as output. Looks nice. We'll go to CyberChef and decrypt the flag. Paste from base64, and there we go. TBTL time of check to time of pwn. So fun challenge. The next pwn challenge is diamonds and rust. So for this, we're given the source code and a binary. In this program, what's going to happen is we supply a username and a password, and if the password matches the admin password, we get the flag. If you search through the file, you'll find a couple of these unsafe things. So presumably we're doing something with these functions, and with these unsafe, it ends up being a buffer overflow. So we have a buffer overflow on the stack, and somehow we have to use that to leak a password. Thankfully, this challenge wasn't too bad if you just like start playing with it and get your hands dirty. It turns out if you just clobber the username, the password leaks out. And the way to clobber it is, for whatever reason, I guess Rust doesn't really have good Unicode support, or I guess, I mean, maybe it does, and that's why people are using this unsafe, but there's been a bunch of these Rust challenges where you just send it Unicode, and like if you say, what is the size of a 32 character Unicode string, it'll say 32, but the actual like bytes is more than 32. I just released a Unicode video somewhere on the channel. I think it was last week, if you want to check stuff out. But anyways, we're just going to send it some Unicode. It's going to do a buffer overflow. And then when it prints it out, it's going to print out the admin secret that is also stored on the stack. And then we just submit the admin secret to the remote process and we get the flag. To see what the self script looks like. Like I said, you just send it after the username. We're just going to send it a bunch of data. So I send 32 poop emojis. I think these are 4 bytes each. And the username has a max length of 32. So it's, like I said, it's going to say that this is, has a length of 32, but the actual bytes is much more when it's in UTF-8. Cool. And then it's going to then print out our username. And as part of that username, it's also going to print out the admin secret because it's just we collaborated the stack. And so it's just going to print out everything until a null byte, I guess. Or actually, it's going to print out the total length. I feel like this challenge is a little bit contrived, but so it's going to calculate or print out the entire length. And then because of that, it'll leak out the password to us. And then from there, we just send back the password to the process and we get the flag. So we can run it, Python 3, solve.py. Whoops. There's one little thing. This is what I did locally, and this is what I did remotely. I guess the stack was maybe just lined up a little bit differently depending on where you execute it, or maybe the password was a different length. I'm not too sure, but basically just grab a different section of password from the stack. But now we can run it, Python 3, solve.py, and we get the flag. TBTL, thanks for offering me secrets in Rust. So fun. The last traditional pwn challenge is heap-peek-and-poke. It says last year's solutions were unattended. Let's try it again. We're given a netcat port, download binary, the source code, libc, and libc++. So that wasn't all the libraries we needed, for me anyways, to actually run the challenge. The libc they gave us was 227. So from that, you can probably guess that they're using Ubuntu 18.04. So I went on to Ubuntu 18.04 and I copied over the missing libraries to get it working correctly. And for me, I was missing libgcc. It just, the linker was, or the loader wasn't happy if I didn't patch the elf. So the first step was doing a pwn init, which I've shown a bunch of times. If you're not familiar, I'd highly recommend downloading it. This will link the correct version of libc, and it'll also download a loader, and it'll unstrip libc for you. So that's step one. Like I said, after that, it doesn't run on Ubuntu 22.04. So I ran patch elf to see what libraries I needed. It also tells you which one's an error. Like I said, then I jumped into a Ubuntu Docker container. I grabbed it out to do that. I'll probably get it wrong, but interactive volume mount, print working directory, mount that to challenge, oops, chal, and then we want down here. Cool. So this is how you can mount it. So it's going to take the current working directory and mount it to the chal folder within the container. So once you're here, you can then do LDD on chal and just copy all the libraries that you need. So this, just copy it to your current directory, and then you have the library. And then you can go back and you can do the necessary patch elves. So we replace the patched version with our local version and the patched GCC with the local version here. Once you've done all that, the challenge should have all the correct local libraries and should run correctly. So that was the setup stage. Cool. So now we can actually start exploiting stuff. So this was the heap challenge based off of the name heap, peek, and poke. The way this challenge works is I'll scroll down to the source code, but I'm just going to explain it. You can issue two different commands, either peek or poke. Peek just means you get to read an arbitrary byte from an offset from some heap chunk, and poke means you get to set a arbitrary byte at that offset. So very simple challenge, I guess. I guess simple to explain. The real challenge was actually exploiting it. I believe all the protections were on. Check sec file chal. Cool. So all the protections are enabled, but they are using a very old version of libc 227. Cool. So just giving a quick overview of how we're going to exploit this. I guess I'll actually do it in GDB. Chal break main run via map. Cool. So we have all the memory segments within the process. So like I said, we can do arbitrary reads and writes from some arbitrary chunk in the heap, but we don't know where anything is laid out. We saw that there was full row enabled on the binary, so we're not going to be overwriting any global offset table entries in here, but they were using an older version of libc, and so because of that, where's libc? Of libc, so because of that, the free hook or the malloc hook are very interesting targets. As part of the program, they also gave us this win function that we can call. So we do have a jump location, but if we have the libc leaked and we're overriding the free hooks, we can also just jump to a one gadget or something. I think I do jump to the win function though. Cool. So step one is we need to find some leaks. So I'm going to run the program, enter in a string. Oops, that's not what I want. So step one, we're going to look for leaks. So the way I did it, there's probably multiple ways. Is I did use the search command within the heap to see if there are any addresses to the main elf or libc. I didn't find any for libc, but I guess I didn't search too hard. Maybe there is. But I did find one for a main elf address that we could use. This. So you do a search 4 bytes, this hex value, oops, and we only want heap results, and we can see there is a leak. So somewhere in the somewhere in the heap, there is a address to the main elf. So what we can do is viz heap chunks, let's set max. So we're going to set the max size. We'll do viz heap chunks. So we are at a bunch of A's. So our offset starts right here. And we saw that if we search for an address at this address, whatever, 8F8A, 8F8A, right here is a address that points to the main elf. So what we can do is calculate the distance from here to here, and then we're just going to print out all of this, and we have our leak to our elf. Once we have a leak to the elf, we know where we have that binary, so we know the offset to a global offset table entry. So we can do a global offset table entry, and we can start reading values from here. And this will give us the leak to libc. I forget which value I leaked. I think I leaked like memcopy or something like that. I'm not seeing it right now, but memcopy. Oh, here's memcompare. That's what it was. Just because it doesn't have that weird C++ syntax. So here's a memcompare. So we calculate the offset from where we were to here. Oh, I guess no, before that, sorry. We also need to leak a heap address because we don't know where our offset is. Thankfully, the Tcache is leaking addresses everywhere. So we can see even right here. So this is where we are. If we just go down, what is that, 10, 20, 30, 40, 50, 60 hex, we have a leak right here. This points to 618. And so from here, we can just, calculate the distance between here, and we know where we are. Actually, This is using a, I just realized technically we're doing it wrong. I'm using chow instead of chow patched. And so this is using a newer version of libc, which has safe linking. So normally this would be a full address to here, I believe, but I'm using the wrong version of libc. But anyways, about that, it doesn't really matter. You can get the leak to libc even with this one too. You just have to calculate it a little bit differently. So we have the heap leak, we have an elf leak. So from there, we can calculate the distance to the global offset table entries. From there, we'll start reading the value here, which will give us a leak to libc. So I'll read this value out. Now we have a libc leak. And so we have all of our leaks. Once we have the libc, the elf, and the heap, and we have arbitrary writes, pretty much game over, except when we calculate or supply integers. Let me go to the code. This is more of an implementation detail, but it is annoying or important. X and Y are integers, and they're 4-byte integers. So the difference between the heap and the main elf is within 4 integers. The difference between the heap and libc is bigger than 4 bytes. So because of that, we have to do a little bit of heap corruption. Thankfully, it's not too bad. We're on 227, so you can just do some tcache poisoning. So you can this heap chunks. What we're going to do is we're just going to overwrite the forward pointer or the backwards pointer, I forget which one. And so that when it allocates the next chunk, it'll allocate a chunk somewhere that we want. And so we just allocate a chunk on the free hook. And so that way, the next time it does an allocation, it's ours. We need to force the program to do allocations. To do that, if you just send it a large line to get line, I think anything like over like 16 bytes or something will allocate a free and a malloc. And to check that, you can also break on free or break on malloc, and you can see how large the chunk needs to be before it calls malloc on your input to store your input. Yeah, so you do that. We've overwritten the free hook, so we're just going to put the win address from the main elf binary in there, and from there, next time it calls free, it calls your code and you win. To see what that looks like, because that was a lot. All standard pwn tool stuff. We grab libc, we connect to remote. At the very start, you have to enter a string. Doesn't really matter. I wrote a little utility function, so this will grab all the bytes from the start to the end. Doesn't do anything too exciting, just reads in byte by byte because we only get a single byte at a time and then just joins them together. I also wrote a utility thing for poke, so this will write from the start an array of data, just goes through and pokes that data in. Like I said, the very first step was to grab that elf leak. We saw that there was an elf leak somewhere in the heap. So we just we calculate that offset. Like I said, it was something like this. The very first time I ran it, I saw where the elf leak was. Here it is. So I take this address, but with an 8 at the end, and then I subtract it from this address, and that's, I don't know, like OX20 or something like that, or sorry, 200 or something like that, whatever that is. And then we do the same thing, but we add 8, so we grab those 8 bytes. From there, you figure out what this address is. So you can do just examine here. So it is some help function. Cool. Or a help string, maybe, not too sure. And then you subtract that from here. And that's what this is right here. And so you get the base of the elf. From there, we calculate the heap address. We could have done this the other way too. But the heap address, I'm grabbing one of these tcache pointers, which points to another address on the heap. And then from there, I'm able to calculate where the base of the offsets are when we're doing the peaks and pokes. From there, we can grab the global offset table entry for memcopy in the main elf, just by peeking at those addresses. So we just take the base of where we are and we subtract it from the global offset table entry that we're interested in. We grab out those 8 bytes. From there, we can calculate the base of libc. I just print out all my pointers, make sure everything's good. And then we assert that the libc base is all good. One minor note, memcopy. So in libc, I think for like performance reasons, it's not always a direct to one mapping. So memcopy with the libc symbol for that is this one. Or sorry, not memcopy, memcompare. This is the actual symbol name on my computer, and it ended up being the same on remote. Cool. And just to clarify, you can see that in the global offset table entries too. Global offset table, read, where was it? Memcompare, we can see this is the actual symbol it's resolving to. Cool. What's next? Now we start triggering. We're going to do that tcache poisoning. So first off, I make sure that there is a allocated chunk of size OX28, I guess, is what I settled on. So I send it a just OX28As so that it does a malloc and a free. So we know we have good chunks there. The next hard part is figuring out where those chunks exist within the heap. This was kind of annoying. What I ended up doing was just since we're allowed to inspect or peek at heap addresses, I just started dumping as much heap as possible until I found those addresses. So I got it working locally, but the offsets were different remotely. So I just dump it all out. This is what it looks like. So at this heap address, which is base plus 2250, we have the size pointer of OX31, which corresponds to this. We have the forward pointer and our data. So now that we know what the offset is, it's this. We can corrupt that forward pointer because it's a linked list, tcache, so that it points to free hook. I think it also does 2 frees and 2 mallocs for some reason while doing these. That's why we only have to do it once. And instead of free hook being null, we're going to say free hook is equal to the win symbol. I forget what this is called. I need to do more research for this, but I think this is like C++ symbol resolution syntax. I could be wrong, but I need to look into it and why it's kind of nasty. But it happens in C++ binaries a lot in C++ libraries. Cool. And then we trigger the call to malloc and free again, so our hook gets executed and we should get the flag. So we can try running it. Python 3 solve.py. Computer says no. I wonder if I change. Oh, there we go. There we go. And it's working. Cool. There might have been like a new line in a leak or something that doesn't line up correctly. So TBTL, unintended solutions are always welcome. So fun. The final Pwn challenge was squeezing tightly on ARM. This was just a PyJail challenge. I feel like it should have been in NISC, but it was here. So this is the server code. It's going to define the flag within source code. There's this like check thing, and then otherwise it's going to eval our code, and we get 10 executions. It sets built-ins to empty, and location is also empty, so not too much going on. For the filter, the command cannot be greater than 120 characters. We're only allowed to use 0 of the single quotes, 1 period, 1 open close, 1 slash, and 1 plus. And that's what this code is doing. So pretty restricted, sort of PyJail. I don't think there's anything, maybe there's an unintended solution that's way better. I just did like kind of the standard sort of PyJail escapes. This ended up being the payload I used, just kind of constructing it out. So we can create brackets, and then we kind of work our way up the property inheritance chain. So class, base, subclasses. I forget what subclass we're looking for. Weak or something like that. There's a bunch of articles online. You just search for it. And then from there, init globals, and you get access to system, and then you can call shell commands. One thing that was annoying is, oh, it looks like I was only off by 1. This is the one that works locally, so you could also ask for the Python version. And so 133 on the Python version worked for me, but it didn't work on remote, so I started fuzzing it from 1 to, I guess I did 1 to 500 or something. I guess it was 132, so I guess I should have just tried off by 1. But anyways, so to get around the fact that you can only use like open quotes, you can only use like 1 period per execution. I think it's called walrus operators. I could be wrong on the name. But basically you can save variables, and normally you cannot save a variable in an eval, but using this like, I think it's called the walrus operator. I could be wrong. You can save variables this way. So I just say A is equal to the start, so class, then I grab base, subclass, I grab the index. Like I said, I was fuzzing the index for a while, but eventually I found it. And then init global system cat. One thing that's what I thought was going to be annoying, but it ended up not being annoying, is you don't get any output. Oh, sorry, I added this sprint as preferred debugging, but normally you don't get any output when you run this. So I thought I was going to have to do it blind, but thankfully OS Systems just pipes it out to standard out, so we didn't actually have to worry about that at all. And so once you're at the very end, you can start doing system calls. Like I said, I thought I was going to be curling or I was going to pray that curl was on the box, but it ends up just being that you can just cat out everything and the flag was in there. And yeah, that was it. So we can run it. Python 3 solve.py. Computer says no. I guess maybe it's back up to 133 now. Weird. Okay. So earlier it was 132 and now it's 133. Same as local. No idea, but cool. We get the flag out, so I just cat star everything, which includes the source code. There were 2 files in there. I think it was one like serve.shell and then the actual like app.py or something like that. So TBTL escaping from Python is not an easy task. Cool. And that was all the challenges. Like I said, fun CTF, had a good time. None of them were too guessy, and none of them were like overly difficult. Feel like most of them, once you know the trick, it's pretty easy to write the solution. You just need to figure out what that trick is. For the rest of the week, like I said, we're moving, so I probably won't do any write-ups for a couple of days. I'm building a new computer, so hopefully I can start live streaming the solution write-ups instead. Last time it's kind of jittery, and I hate waiting like 30 seconds to a minute for Geecher to load when I'm trying to like live stream and run Docker and VM. So I'm building a computer in the next couple of weeks, so maybe I'll do some live streaming after that. Otherwise, cheers, and I'll see you at the next CTF.